Thank you for joining us today. My name is Mondo Mikhail. I am your podcast moderator. Today we have a very exciting topic that we're discussing. It's called functional safety. Now, I know what you're probably thinking, but hold on, there's a lot more to this than meets the eye. My very interesting guest today is Darshan Raj. He is Technical Hardware Product Manager at Intel. Darshan has 23 years of industry experience in a wide range of fields, including aerospace, post-silicon validation, digital TV, automation, industrial controls, and robotics. He's had many roles in hardware, software, product integration validation, systems engineering, and now he is the product manager for robotics and industrial controls at Intel in their Germany facility. Darshan, hello. Thank you so much for joining us today.
Thanks, Mamdouh. Thanks for having me.
Of course. Now, functional safety. I have to admit my own ignorance in this topic. If someone told me, "Hey, Mondo, what's functional safety?" My obvious answer would be, "Hey, you got to wear a hard hat on the job site. You got to make sure your chemicals in your office are secure. You have to have cameras around your building in the evening to make sure that nobody breaks in and steals your things." I really didn't understand the depth and also the nuances of functional safety and why it's important. Help us understand what functional safety is and some of its really key concepts.
Mm-hmm. You brought up a very important point. Often people mix up safety with security, and there are languages in the world where safety and security have the same term as well. So understand what you mean. Fundamentally, functional safety can be described as absence of unreasonable risk in case of any hazards that result in malfunctioning behavior of electrical and electronic systems. So this is the fundamental definition of functional safety. What it means is we look for reducing the risk, where a risk is probability of any harm or any destruction happening. So the point is to bring down the probability of such a damage happening. And if you look at functional safety and when we speak of risks, the risks of any injury is measured in terms of severity. Is it someone will lose a fingernail, or will it be a finger, or is it even severe than that? The next is how often will such risk exposure happen? So will that happen once in 100 years, once in 1,000 years? So for example, a meteor strike is probably 1 in a million year probability. So that's a very low probability of exposure. So the next is how often is it to avoid? So if you are dealing with any system, is it easy to avoid a risk? So can you prevent that? If you take away the object, will the risk come down? If you do something else, can the risk come down? So how often is it to avoid such a risk? And the last parameter is the probability of unwanted occurrence. So is it happening unnecessarily? Is it happening without any provocation? Is it happening without any control? So these risk parameters, you actually can arrive at a specific safety level. So fundamentally, with functional safety, you're focusing on reducing unreasonable risk, and you deal with risk with these very specific parameters, and you look for bringing down the exposure of such a risk to people.
All right. That really encapsulates the concept. What I didn't really understand is Intel being the premier CPU designer, microchip designer, and fabricator in the US. Being at ADLINK, we provide enabling hardware. What I didn't really realize is how functional safety is actually baked down to the chip level, to the silicon level. I didn't realize that Elkhart Lake, Tiger Lake, Raptor Lake, these all have features down to the silicon that really enable functional safety and how it's implemented. Can you help us understand that?
Oh, yeah, that's a good point. In fact, I'm glad that you actually know the processor names Elkhart Lake, Tiger Lake, and Raptor Lake having these functional safety specific features. What Intel has been doing for the last 4 years or more is bringing together a collection of safety integrity technology within the processor. So what this does is you have a specific collection of IPs, intellectual property features, that you add in to the processor. With that, you automatically are able to check the execution of various instructions. So you are able to check the sanctity of the instructions being executed. And in case there is a mismatch or if there is a fault, you'll be able to at least flag that something went wrong. So as part of the safety integrity technology, Intel processor has added these features as part of the processor design. And with that, anyone who's running their safety software on it with these specific features enabled will be able to automatically determine if these instructions were executed as anticipated, as expected. And in case if there is a mismatch, the processor will be able to flag a fault to help the overall system to take corrective action.
Right. So how has the market helped evolve functional safety? What market needs did Intel see that made it imperative that functional safety needs to be baked into its processors, or how you manufacture these processors, the new manufacturing processors that keep shrinking or lower power, hopefully reduce costs in the long run? Also, how has functional safety evolved in the workflow when people are actually doing their jobs? Let's say at a industrial automation site, product comes in, product is moving, it's used. Robots move products. Robots are assembling products as they move further down the assembly line. So what market needs help drive functional safety, and how is that actually being implemented into industrial automation workflows?
For this, probably I'll take a step back and introduce what Intel has been doing for a last decade or so. So Intel has been a pioneer, has been spearheading this conversation and transition in the manufacturing sector for a workload consolidation and a software-defined system. So what this means is traditionally industrial controls had multiple small microcontrollers which had fixed function operations, which also kind of matched with the kind of sensors and actuators that they were dealing with. What Intel has been spearheading is the conversation of converting these fixed function dedicated microcontrollers and converting those workloads into a software-defined workload consolidation system where all these workloads can be run on specific industrial features-enabled microprocessors that have been available as part of a last multiple generations. It's a logical transition considering that the industrial manufacturing and factory floors are going towards automation. It's a logical transition that all workloads that are available on a specific platform are converted into a software-defined system. So we have a real-time workloads, we have various PLC workloads, programmable logic controller workloads, and the next one is the function safety workloads that can be brought together into a software-defined system. The outcome of such a system is you actually have a system or a platform with reduced bill of materials, reduced BOM components. You're able to come up with a system that is able to recover well. You have reduced maintenance cost. You're able to design a system that can be up and running. You can increase the high availability of such a system for factory operations. So the transition from a fixed function, a dedicated microcontroller, or a small hardware PLC systems to a software-defined workload consolidation system running on an Intel processor with a lot of technologies and IPs that have been added into the processor is the way to move forward if you're looking for a factory floor that is autonomous and is looking at a reduced maintenance cost with high availability, as well as able to recover and heal itself in case there is a fault. So this is the transition which motivated and has been motivating Intel to take this to the next level.
Right. I know at ADLINK, I mentioned previously, we build hardware-enabled technology, but some of that involves freestanding cameras, whether it's our Neon camera that has an Elkhart Lake processor that has an Intel VPU built inside. Some of the boxes we have power over Ethernet, so you can put cameras directly into. They process the information on our Intel processors and so forth. Today, what we see that's proliferated all around us is cameras. Everywhere we go, it seems like we're being monitored. That camera data or that input data is being heavily processed using AI. AI has really greatly impacted us on a daily basis. How has AI, specifically vision processing and AI on that vision data, really impacted functional safety, and where is it taking it?
That's a terrific question. AI is the buzzword of the day. And you bring in the topic of vision systems. So cameras and vision inputs are becoming important part of the sensor data that is used for safety. So we have the classic LiDAR that is often used, as well as the infrared sensors, as well as the standard color cameras as well. So traditionally, these data points give us either a two-dimensional data point or a three-dimensional point cloud. So Intel has very powerful CPU processors, and to be able to process these 2D data or a 3D data, point cloud data on a processor is possible with a deterministic latency. And that's a benefit of running these workloads on a CPU. Having said that, you brought up an interesting point of AI. AI traditionally has been classified as the machine vision, the classical computer vision algorithms, which are very deterministic, more or less algorithm based. And for a given specific input, you have a specific output that is deterministic. But you also have the most often that is coming across is the deep learning or the convolution neural network models that are probabilistic, and they have a bit more variance in their outcome. If a small parameter changes, the probability or the outcome has its own differences. So there have been studies ongoing in the industry as well as in the safety standards to incorporate these AI workloads as part of the safety standard specification and definition. However, with the current machine vision and computer vision algorithms, a well-defined software architecture, you will be able to run them and achieve the desired AI capabilities on an Intel compute in a deterministic fashion in a much better way.
Right. I also really wasn't aware of the software capabilities Intel brings to the table. I didn't know about AVID software package, which monitors repetitive processes. I didn't really know FuSa AI. It's a no-code computer vision platform. Also, Getty, it's a training platform that automates the training of computer vision applications. That coupled with the processes, coupled with the hardware that has functional safety baked into the CPU, and of course, coupled with technology from companies such as ADLINK, it's really a very nice marriage in moving forward. So how does someone start with their functional safety journey? If I'm a CEO or if I'm an executive in a company, I have to admit there's a lot of people out there who really didn't grasp what functional safety truly is. How would you impress upon me that I need functional safety to implement functional safety? What are the benefits for me, bottom line, in my organization? And then if I was still curious, how would I actually get started? How would I delve into Intel? Who would I contact?
Mm-hmm. So you actually mentioned multiple points here. On the software front, a typical standard commercial software is something that is used on the normal control operations, whether it is robotics or in the industrial controls. For the functional safety side, the software should reach a specific quality. So based on the safety target that someone is considering, you will either have to have a good quality software, or you have to qualify the software to a specific target, safety target that someone is considering. So that's a fundamental difference between the safety software as well as the non-safety software. So having said that, to your second point, I would look at functional safety that will stay, that was there yesterday, that will stay today, and that will continue to evolve tomorrow as well. But what benefit functional safety fundamentally brings is eliminates risk, or at least the defined probability. It will eliminate the risk of injury for human beings or the damage to the objects for the equipment that it is operating in the vicinity of, which brings in other parameters in terms of liability, in terms of complexities, in terms of replacing equipment or other maintenance challenges. But the bigger picture here is, once you are bringing together a workload consolidation angle for functional safety that works in tandem with the normal control operations, you are able to bring together both narratives and come up with almost autonomous or a fully autonomous factory floor that is able to reduce downtime, increase availability, increase recoverability, where you can heal from a fault or a failure, and it will reduce the operation cost and the maintenance cost. Not only that, but if you are deploying a specific robot or a mobile robot in your factory floor, you can seamlessly, with zero touch or no touch, are able to bring it online. Whether you are deploying this, it's likely the same autonomous mobile robot that you're deploying it on a warehouse, or you're deploying that at the finished part of the assembly line. So based on the location where this mobile robot is operating, you may have different targets for its control operations as well as safety operations. With a workload consolidation and software-defined approach, you are able to configure and provision these robots automatically based on the workload that they are targeted, which significantly reduces manual effort and also makes it mistake-proof, or reduces the possibilities of making mistakes when doing such a thing from happening. So it completely eliminates the intermediate steps where something can go wrong.
Darshan, this was a really fascinating journey for me. And I opened up saying I didn't understand much about functional safety, or I thought I understood it, but it ended up taking me down a journey that it was really refreshing and very exciting. Thank you. I hope everyone listening found this as exciting as me in starting their journey in functional safety, its understanding, and sees the relevance in implementing it in their current environment. Darshan, thank you so much for joining our podcast today. This has been really exciting. I want to thank all of our listeners for tuning in, for having a little bit of curiosity about this enough to listen to the podcast. And we really hope you join us for the upcoming exciting podcast from ADLINK. Darshan, thank you very much for joining us.
Thanks, Mamdouh. And please reach out to your local Intel sales representative for more details. They'll be glad to help you.
Thank you.